Okay, a little video just to explore in a little bit more detail what we've looked at in the last video, where we're going to have a look at repeated and complex eigenvalues for a 2x2 matrix. So there are two possible situations which can arise from repeated eigenvalues. Either we end up with a case where there's only one eigenvector, or we have a case where there are infinite eigenvectors. Okay, it's either one or the other. Usually we would have two eigenvectors if there's two distinct real eigenvalues, or there'd be no eigenvectors, or at least no real ones, in the case where there are two complex conjugate eigenvalues. But when we have repeated, we either have one eigenvector or infinite eigenvectors. Okay, so case one, one eigenvector. This occurs when we have, for example, a skew. Okay, so a skew is a case where we only have one eigenvector. So let's just go through the motions to prove that this is true for this matrix here. So to calculate the eigenvalues, what we're going to do is we're going to calculate the determinant of 1 minus lambda, 2, 0, 1 minus lambda, and that's going to be equal to 0. Okay, so solve this equation. That is 1 minus lambda times 1 minus lambda minus 0 times 2. We want that to equal 0. And we can see that this is a repeated eigenvalue. Lambda equals 1. It's the only one. Okay, so this is the only eigenvalue. Okay, so let's try and calculate its corresponding eigenvector. So when lambda is 1, we're going to end up with 1 minus lambda is 0. That's a 2. That's already a 0. And 1 minus lambda is 0. I'm going to times that by the vector xy. And we want that to equal 0, 0. So we have matrix subtract lambda I times the eigenvector is equal to the 0 vector. So that's going to give us 2y equals 0. And it's going to give us 0 equals 0. So we require y to be 0, and x then can be anything. So 1, 0 then is the obvious choice for that. So 1, 0 is the only eigenvector. And when I say it's the only eigenvector, I mean that direction is the only eigenvector. Obviously 2, 0 and 3, 0 and 4, 0 and 5, 0 are also eigenvectors, but they are the same direction as this eigenvector. So it's only got one eigenvector because it's the direction that we care about. Okay, so that's the only eigenvector for this matrix. Okay, we haven't got another lambda value to sub in. Okay. Case 2, that's going to occur, for example, when we have enlargements. So we're going to enlarge the 2D space centered on the origin. That's represented by this matrix here. And let's give a number to n, to a. Let's say we're going to enlarge by a scale factor of 3. So let's do 3, 0, 0, 3, just to make it a numerical example. But you can apply the same theory to any letter a. Okay, so we're going to calculate the eigenvalues of this matrix. So that's going to be the det of 3 minus lambda, 0, 0, 3 minus lambda. So I've subtracted lambda from the lead diagonal here, set the det to be 0. That's going to give us 3 minus lambda squared, subtract 0 equals 0. And again, we can see we've got a repeated eigenvalue situation. In this case, it's not 1, it's any. It can be anything, it could be a. In this case, it's 3. So again, we have a repeated eigenvalue case. All right. So subbing in lambda is 3 into this matrix here gives us the null matrix 0, 0, 0, 0 times by my eigenvector xy equals the 0 vector 0, 0. And that gives me that 0 equals 0 and 0 equals 0. That is true for all x and y. Therefore, there are infinite eigenvectors because any vector you choose will satisfy those two equations because x and y don't come into it. So any vector chosen will be an eigenvector, except for the null vector. We don't say that. We don't include that in this list. So, for example, we could have the vector 1, 0, or we could have 2, 1, or we could have 0, 5, or we could have -3, 8, or we could have anything. Any two numbers, as long as they're not both 0, will be an eigenvector for this case. And we'll see a similar case in 3 dimensions where there'll be a repeated eigenvalue, and you can choose any two eigenvectors in a particular direction, and then there's infinite numbers. You can add those together to give you a new eigenvector. We'll see that when we get to 3D. But for now, 2D case, lambda is 3 for this enlargement. Any vector you choose will be an eigenvector. Okay, so that was the cases where we have repeated eigenvalues. You either have one eigenvector, like you do with a skew, or we have infinite eigenvectors, like we have with an enlargement. We can have complex conjugate eigenvectors. I did mention this in the previous video. We're not going to delve into it in a huge amount of detail because on this course we tend to stick with everything real within matrices. But it's worth knowing that this is a thing. It does exist. A rotation matrix will have complex conjugate eigenvalues unless you have theta is 0, in which case it's the identity, or theta is 180, which is the same as two reflections, one after the other. So we tend not to consider those two cases as reflections, as rotations. When I say rotation, I mean theta is something that's not 0 or 90 or 180. So I will make a note of that. So usually for theta not equal to 0 or 180, just because then it can be looked at as not just a rotation but something else instead. So if you have an actual rotation, then you're going to end up with a complex part to the eigenvalue, which means you're going to get complex eigenvectors. Like I said, I'm not going to go through this and calculate the actual eigenvectors, but you can do that. You can take cos theta plus I sine theta and calculate the eigenvector up here, but it will be complex, but that's fine. We can deal with complex numbers and such, but it is above the scope of the course as a general rule of thumb. Okay, and then finally, I do want to make note that it is possible to have an eigenvalue of 0. So this will only occur when the matrix itself is a singular matrix, i.e. there's no inverse, and that's because when you come to do the det of m minus lambda I, so 4 minus lambda in this case, 6, 2, 3 minus lambda. If we want that det to equal 0, and the det of that is already 0, then lambda equals 0 will come out as a solution to that, which is fine. That's completely allowed. You can have an eigenvalue of 0. So let's continue with this example. Let's see where it goes. We're going to end up with 4 minus lambda times 3 minus lambda minus 12 equals 0. That's going to give us lambda squared. Then we've got minus 4 lambda minus 3 lambda is minus 7 lambda, plus 12 minus 12, which I'll write for completion. Plus 12 minus 12. Those two will obviously cancel, and we're left with lambda into lambda minus 7. So in this case, we have two lambda values, 0 and 7. And we just carry on the process as normal to calculate the eigenvectors. So when lambda is 0, we will have 4, 2, 6, 3 times our eigenvector will equal the 0 vector. And we're going to end up with 4x plus 6y is equal to 0, and 2x plus 3y is equal to 0. This is the same line as we would expect for this calculation. So we're going to end up with y is equal to minus 2/3 x. And then any two numbers which satisfy that equation will give you an eigenvector. So I'm going to choose x is 3 and y is minus 2. But any non-zero multiple of that will be an eigenvector of this matrix with eigenvalue 0. And then using lambda as 7, we're going to end up with 4 minus 7 is minus 3. We've got 6, 2, and then 3 minus 7 is minus 4. And we're going to times that by our eigenvector xy, and that's going to equal our 0 vector. And we're going to end up with 2x minus 4y equals 0, or if you like, x equals 2y. I just did the bottom line, but the top line will give you the same equation. Okay, x equals 2y. So we just need to choose a value for x, choose a value for y that satisfies this equation, and that will be your eigenvector. So the obvious choice would be 2, 1. But any non-zero multiple of that vector will be an eigenvector with an eigenvalue of 7. So just because lambda comes out as 0 as being an eigenvalue, it doesn't stop anything. It just carries on exactly as it would have been when we had a case when it wasn't 0. But I did want to highlight that it is possible, of course, to have a lambda value of 0. What's actually happening with this matrix here is it's taking the whole of the xy plane and it's crushing it down onto this line through the origin, which is why it's irreversible. Multiple points in the xy plane will go to the same point on this line, which is why it's you can't reverse that process. But yeah, and this vector here, everything on that line just gets crushed to the origin. So that's an example of all of those points on that line under this matrix transformation will arrive at the origin because the lambda value is 0. So it just snaps down to the origin, and every other plane, every other point on the plane snaps down to its own point as well. All right, I'm going to stop there. I've waffled on enough. I think next video we're going to be delving into some 3D stuff. That's all the 2D theory that I could possibly cover. So I hope you found it useful so far. Please drop any comments that you have in the comment section below, and I'll get back to you when I can. Thanks very much for watching.